Okay, so welcome back. My name is Shahar1. I'm a staff member at the Geophysical Lab. I'm an experimental isotope geochemist, which means that I conduct high pressure and temperature experiments, but I probe the experiments for their isotope ratios of the different minerals or compositions inside them, instead of more traditional experimental petrology, just looking at mineral assemblages. Normally, I focus on the early solar system, but today I'm going to focus on the deep Earth. So I'm going to, the basic outline of the talk is that the first 10 to 15 slides are going to be very introductory, fundamentals, basic stable isotope geochemistry. I have no idea how many of you have ever taken isotope geochemistry, if you remember anything about it. And so I'm going to try and just walk you through the very basic fundamental aspects of it for the first part of the talk. And then I'm going to show you some applications of the equations that I'll show you in the beginning. I'll show you the applications towards the end so that you can see how we actually use stable isotopes to discuss problems in the earth sciences. So very simply, stable isotopes, right? An isotope has an extra neutron of different elements. So carbon has 12 and 13. 13 has one extra neutron from 12. When you talk about stable isotope geochemistry, for everything other than the last 10 years, you're talking about these elements here: hydrogen, carbon, nitrogen, oxygen, and sulfur. These are considered the traditional or the light stable isotopes. And in stable isotope geochemistry, what we do is we look for elements that have more than one stable isotope. Okay? The reason we look at more than one is that we're always looking at ratios. The reason is that when we analyze samples through a mass spectrometer, we can't get an absolute value for the amount of one isotope, but we can get a ratio for the ratio of two separate isotopes of one element. Okay, so we're always looking at ratios. And it says here the difference between isotopes has to be a significant fraction of the atomic mass. And this is a technological problem, right? You want to be able to measure the number of atoms, or the isotopes. And if you only have like a few atoms coming through your mass spectrometer, you're not going to be able to measure enough. And so this value of enough to measure, right, has changed throughout the years. But for many, many years, the isotopes that were measured were hydrogen, carbon, nitrogen, oxygen, and sulfur, the isotopes of those elements. What does fractionation mean? Every time you hear an isotope geochemistry talk, you're always told a fractionation between different minerals, right? A fractionation simply means the partial separation of two isotopes of the same element into different reservoirs. Stable isotopes are the same always in terms of their abundances. They don't change like radiogenic isotopes do, right? They're not a function of time. The stable isotopes we had at the beginning of the solar system are the stable isotopes abundances we have today. Okay, so chemical and physical processes are what are changing the ratios and are causing this fractionation between different reservoirs. The reservoirs could be minerals, it could be rocks, etc. And isotope fractionations occur due to either an equilibrium or kinetic fractionation. My entire talk is going to focus on equilibrium fractionations. Okay? Kinetic fractionations are due simply to the fact that light isotopes move faster. Because isotopes will have the same kinetic energy, the difference in mass will cause a difference in the velocity. So light isotopes will move faster. Kinetic fractionations are unidirectional, okay? So diffusion, evaporation. In these cases, the products will always be light because it is easier to break a bond with a light isotope than it is with a heavy isotope. Biology will tend to, organisms will tend to incorporate the light isotopes. It takes less energy for them to break the bond with the light isotope than it does with the heavy isotope. Okay? That's all kinetics. I'm going to focus completely on equilibrium. And the reason is that in order to understand the fractionations in kinetic systems, you need to really understand the equilibrium ones first, and then you can decide whether or not your system is in equilibrium, and if not, what kinetic effect, process it has gone through. Okay? So why are there differences? Why is there an equilibrium isotope fractionation? It turns out it's a purely quantum mechanical effect. In classical mechanics, chemical reactions are affected purely by electronic configurations. Isotopes have the same electronic configuration as each other. Okay? All elements have one electronic configuration. But in quantum mechanics, the mass will have a vibrational frequency. And when you have a different mass, you will have a different vibrational frequency. And isotopes, by definition, have different masses. Okay, so the equilibrium isotope fractionation is a quantum mechanical effect. So if we look at a cartoon, right, of a potential well, energy, interatomic distance, energy is quantized, okay, into discrete levels. And at the 0 point energy, when n equals 0, the energy is equal to the Planck constant times the vibrational frequency. The vibrational frequency is a function of the reduced mass. So now we've introduced mass. Therefore, isotopes have different vibrational frequencies. Even at the 0 point energy, okay? Even when nothing is excited, everything is stable, there will still be an equilibrium isotope fractionation due to the energy difference of these vibrational frequencies based on mass. So very simply, right, and this is obviously extremely exaggerated, the heavy isotope will have a lower vibrational frequency than the light isotope because it's heavier. Okay? Sorry. Now imagine we're in a chemical reaction and we have suddenly a mineral that has a stiffer bond than the previous mineral. When you have a stiffer bond, you're changing the force constant, the spring constant. Okay? So you have a slightly tighter potential well. In both cases, your vibrational frequency is going to increase, but the system's going to want to minimize energy. And so the heavier isotope will tend to be associated with the stiffer bond because it doesn't increase as much as the lighter isotope. And stiffer bonds are associated with shorter bonds, higher oxidation state, lower coordination number, et cetera, et cetera. Okay? But these are the ones that are most normally focused on. So what we know, right, is that based on quantum mechanics, the heavy isotope will tend to be concentrated in the stiffer bonds. So in 1986, in a Reviews and chapter, O'Neill tabulated 5 common characteristics that are shared by elements that show large variations in isotopic compositions in nature. Okay? And in 1986, the isotopes that we're referring to are the ones that I showed you earlier, the elements hydrogen, carbon, oxygen, nitrogen, and sulfur. Okay? So they have low atomic mass. The relative mass difference between the isotopes is large. These two go together, right? The tendency to form covalent bonds, because they're stronger. Elements exist in more than one oxidation state, like I was just telling you. And the abundances are high enough that we can measure them. Okay, so this is what we knew as basic rules of stable isotope geochemistry in 1986. And this is an example from Bob Clayton's group in Chicago in 1975, where you're looking at the difference in the vibrational frequencies and the bond lengths of methane between hydrogen or deuterium. And you see there's a pretty big difference in these vibrational frequencies, whereas over here, when you're looking at the difference between oxygen-16 and oxygen-18 in the carbonate ion, that difference is smaller. So you can imagine as the isotopes get heavier and heavier, this difference gets smaller and smaller and smaller. And this is one of the reasons that people have always focused on the lightest elements, because the differences are larger. Okay? Okay, so that was the big picture graphical way of looking at it. For those of you that are more mathematical, these are the actual equations, okay? So we have, and a lot of this is stolen, by the way, from Bill White's geochemistry textbook, so you can read it if you want more information. So you have a reaction where the prime here is the light isotope, okay? So we have the light isotope going from mineral A to mineral B, and the heavy isotope going from mineral B to mineral A. We just have an exchange of one isotope, okay? The equilibrium constant for the reaction, in a quantum mechanical sense, right, is equal to the partition function. The partition function here, Q, is the sum over all the energy states of that molecule of the probability that that molecule will be in a certain state. Okay? So it's the partition function of the products over the reactants. The partition function total is the product of the translation, rotational, and vibrational movement of the molecule. Now, this is based on an ideal gas. Okay? So ideal gases move translational, rotational, and vibrational. Okay? Solids don't do this, but this is the way that the theory was developed. So this is what I'm going to show you.
Now, is it obvious why it's the product and not the sum?
The Q total?
Yeah.
I don't know, honestly. Maybe Bill knows.
What was the question again?
Why is this the product and not a sum?
Let's see. It has to do with Gibbs free energy being exponentially related to that's my simple explanation. The distribution coefficient, or excuse me, the equilibrium constant K. Okay, so there are. That would be the short answer. In thermodynamics and in mechanical statistical mechanics, often things are multiplicative when you might think they should be.
It's actually
additive.
It's a concatenation, right, of probabilities.
Right.
And so
That's right. That's right. It's because of the probability. And it's actually really important that it's all a product because, as you'll see, because we take ratios, a lot of things will fall out and they'll cancel. So it's good that it's that's right. It's a probability. So as you can see, though, when you're actually looking at translational, rotational, and vibrational energies, the vibrational energy tends to be the largest in these systems. Okay, so we'll do one by one, and what you'll see is that the translation and the rotational are basically going to fall out, and we're going to be left with only a vibrational frequency that's going to matter for this equilibrium constant. Okay, so for the translational, it's equal to 2 pi mass times, this is the Boltzmann constant, temperature, Planck constant, volume. Okay, when you take ratios for two isotopes, everything cancels except for the mass. Okay, so you have the light isotope over the heavy isotope. For the rotational, same sort of thing, where you have here, I don't know why it's doing that, sorry. You have the moment of inertia, which is the only thing that's going to stay, because the moment of inertia is also a function of mass. Okay, so and here the S is the symmetry number. So if you think about like a planar molecule, the symmetry number will be 1, for example. And then the vibrational frequency is going to stay as is. The partition function for the vibrational part is a function of the vibrational frequency and of temperature. Very importantly, in this equation and in this equation, the temperature cancels for the two isotopes. But in this equation, it does not. So vibrational frequency is very much a function of temperature, and therefore the vibrational partition coefficient or partition function is very much a function of temperature. So if you multiply all these together, this is what you're left with when you take the ratio. There's this theorem here called the Redlich-Teller theorem, or a spectroscopic theorem, or product rule, which basically gets rid of the moment of inertia, and you're left with this equation for the ratio. Okay, so now what you see is that everything has fallen out except for this vibrational term, which is a function of temperature. But okay, so that's the basis of what people the theory for stable isotope geochemistry until 1947, when two very seminal papers came out, one by Urey and one by Beagleisen and Mayer. And what they did is that they took those equations and they made them more applicable to what we can actually measure in the lab and what we can actually see in nature. And so a lot of the variables that I'll show you from now on are ones that we actually use today in stable isotope geochemistry. So the alpha is the fractionation factor. It's the difference in the ratios of the isotopes for two different minerals or materials. And delta, which you'll see all the time, is the ratio of two isotopes in a sample over that in a standard minus 1 times 1,000. We multiply by 1,000 because the numbers are really small, and we always ratio to a standard because, as I said, mass spectrometers will fractionate your sample just by themselves. And so if every lab has a different mass spectrometer that has a slightly different fractionation, you'll never be able to know what the true value is of the ratios that you're looking for. And so what we do is we have international standards. And so we all run these international standards through the mass spectrometers and compare them to our samples, and therefore you can compare values from one lab to another, okay? When you subtract two delta values, two little delta values, you end up with this fractionation, okay? This is called the big delta. And the big delta is just the little deltas of two minerals. So the difference in fractionation between two minerals, or two phases. And this is the equation that I mentioned earlier that was developed by both Urey and Beagleisen and Mayer. And so what you see is that the fractionation is a function of 1 over t squared. Okay, that's the important part, and a function of 1 over mass. This is why I said earlier that the higher the mass, the less the fractionation, right? These are in the denominator. And fractionation is a function of 1 over t squared. So temperature plays a huge role in stable isotope geochemistry. Okay? And this is the equation that explains 2y. And this equation falls out of the equations I showed you earlier through a lot of just math, which I didn't want to derive here, but we recently derived in a paper last year that I can send you if you want. Or you can go to the original paper of 1947. Okay, so based on this equation, there's one more thing I want to tell you. You're going to see beta, okay, in some of my slides. Beta is the reduced partition function ratio. So I just showed you partition functions. Why is it called the reduced partition function? Well, in isotope geochemistry, we really only focus on vibrational partition function. We don't worry about the translational and the rotational. So it's called the reduced partition function because we're only focused on the vibrational partition function, and we're only focused on one element, okay? So the partition function is a sum or average, right, of all of the energies in that mineral. But for isotopes, we're only concerned with the element of interest. So beta is, we don't use equilibrium constants, we use beta. So beta is the reduced partition function, and I'll show you plots of beta later, and I'll explain it to you again. So in 2004, our Reviews in Mineralogy chapter, Edwin Schaubel suggested the following rules governing equilibrium stable isotopes. So this is basically a follow-up to the O'Neill paper, but 20 years later. Okay? So again, stable isotopes will decrease as temperature increases, right, as a function of 1 over t squared. The fractionation scales with mass. You can see that here. And then heavy isotopes of an element will tend to be concentrated in substances with stiffest bonds. This is the bond here, okay, with high spring constants. You have high oxidation state, high covalent bonds, low coordination number. For anions, high oxidation state to which the element of interest is bonded, bonds involving elements near the top of the periodic table, and low spin electronic configurations. So this was all laid out in this chapter. And then he writes, it's important to point out that these rules, particularly 3 and 4, which is this entire section here, okay, are largely untested, okay, with respect to fractionations in the less well-studied elements. That is everything other than those 5 that I showed you before, including in many ways, in many cases, also those 5, okay? So what I'm going to show you for the rest of this talk is ways in which we've tried to test whether or not this is true, and times when it's worked and times when it hasn't. So what can we learn from stable isotopes about the deep Earth? When I was first asked to give this talk, if you remember Michael's question to Uli earlier, there's no rate, right? So how can you talk about flow when there's no time dependence? Well, stable isotopes, by definition, don't change with time, okay? But they're wonderful tracers. They're wonderful tracers of chemical and physical processes that you can then use to talk about things such as flow in the deep earth. Okay, so I'll try to show you examples of that. So what we can do is we can do experiments where we determine fractionation factors as a function of temperature, pressure, and composition. The lab is a really good place to do these sorts of things. We can pick up natural samples where we can determine what the isotope ratios are in different rocks, determine whether or not they equilibrated or not, and if so, what chemical or physical process they've gone through in order to get the ratio that we measure in them. So they're really wonderful tracers. Okay, so if I had given this talk 20 or even 15 years ago, I would show you plots like this, okay, where this is one of the most traditional ways of using stable isotope geochemistry in a high temperature process. I should add, because of the 1 over T squared relationship, most of the work done in stable isotope geochemistry is done at low temperature. But in this talk, I'm going to be focusing only on high temperature, right, because we're interested in the deep earth. So these are experimental, done mostly, most of the experimental work on isotopes was done in the 70s at the University of Chicago by Bob Clayton and his group. And what they've done is they've looked at this fractionation factor. So this is basically the difference in the isotopes, in the isotope ratios of oxygen between quartz and magnetite. Okay, so quartz magnetite is here, albite magnetite, anorthite magnetite. You notice magnetite is lighter than all these other elements, right? So what that's telling you is that the iron-oxygen bond is not as strong as the silicon-oxygen bond. Okay, very simply. As a function of temperature. So you see here at 1,000 degrees, we're getting to the limit where these values are getting very, very small. But what people did for many years is they would go into the field, they would pick up a rock, they would measure the oxygen isotope values of 2 minerals in that rock, and then they would tell you what temperature that rock or that mineral, those minerals crystallized. And they would do this for different mineral pairs, and if they got the same temperature for all the different mineral pairs, they would say this rock formed at this temperature in equilibrium. Okay, so that's thermometry. That's how people used oxygen isotopes. I also took this from Bill White's textbook. The reason is that I was his student at Cornell, so I have all the notes right. So this is a histogram of oxygen isotope values of olivines and clinopyroxenes in different settings. Okay, and what you see is that there's this clear distinction between the two minerals. So this is what I was just telling you. You also see that the range isn't super high compared to the error. Okay, so you would say the Earth is homogeneous for its olivine and clinopyroxene values. Maybe. I don't know. Right? But if you look at whole rocks, you see that morbs have a very tight value, right? So you can say, okay, morbs are pretty distinct in their values and they're homogeneous. But the subduction-related values are slightly higher. OIBs tend to be like morbs but have slightly more scatter. And so what people would do with these types of data is they would try to say whether or not the Earth was homogeneous, whether you could find mantle heterogeneity in rocks. For example, olivines and whole rocks from Hawaii tend to be slightly lighter than other places. And so is that heterogeneous mantle? Is it metasomatism? Is it a bunch of other chemical and physical processes that could change the stable isotopes? Okay, so what you do is you do experiments in the lab, you figure out what the fractionation factors are, then you measure a natural sample, and if you don't get the same fractionation, you come up with reasons why it's different. Another example is in diamonds. And so carbon isotopes are another. Oxygen and carbon and nitrogen and hydrogen and sulfur have had an enormous amount of work done on them. And one of the really interesting ones for carbon is looking at diamonds. So if we look at first whole rock mantle xenoliths, this is all data for mantle xenoliths and separated minerals. And what you see is that there's this spike at approximately minus 25 and another spike at about minus 5. Okay? A lot of people people didn't understand why this was. And so one hypothesis was that, well, maybe this is the higher temperature carbon isotope value, and this is lower temperature. But if you look at diamonds, so diamonds are this amazing tool for Earth scientists because they give us a glimpse into the deep Earth, which we don't have otherwise, right? They form at sometimes very high pressure, lower mantle conditions, and then they get shot up to the surface, and we have them, and we can measure them as basically the only samples we will ever get, I think, from the deep Earth, okay? So they have inclusions in them that can tell us where they came from. Sometimes the inclusions will show that they came from lower mantle conditions, okay? So if you look at where diamonds formed and what their carbon isotope measurements are, you see that if you look at all diamonds, there's this peak at -5, okay? This is considered the mantle value. So -5 is what most mantle rocks will have in terms of their carbon isotope signature. But you see that there's this tail, okay? And this tail is important. If you break up the diamonds into two types of diamonds, meaning which rocks they were found in. So some diamonds are found in eclogitic. They're called eclogitic diamonds because they come from eclogites. And some diamonds are pritatitic. You notice that the eclogitic ones are the ones really with this tail, whereas the pritatitic ones don't really have this tail. Well, eclogites, right, are basically high-pressure basalts. And so it's thought that these diamonds are showing recycled carbon from the surface of the Earth because it's light, because it's organic. So the surface has very light carbon. So it's thought that these light values from the surface are being subducted, brought down, and then the diamonds that are formed are inheriting that carbon isotope value.
And I think you need to emphasize that to get to carbon isotope ratios of -20 to -30, the only way we know that is biological, is photosynthesis or
from the
chemosynthesis.
surface.
On the surface, but specifically biological.
Yes,
right?
Exactly. Because what I was telling you earlier, right, is that biology will always choose the light isotope because it's easier to break that bond. And so the lighter and lighter and lighter the organisms will continue to, the organic carbon will continue in that direction. And so -20, -25, right, that's probably also been mixed. So it might have started out even lighter, right? But that's what these light carbon isotope values are telling you. We think that there was this subduction of organic material. It went into the mantle. Diamonds were formed there, and then it's getting shot back up to the surface. Okay?
Does that mean that the light isotopes are not getting into the deep mantle?
Well, okay, lower mantle diamonds, right? There are a couple. Okay, so I study core formation. So when I look at this, I want to know what the carbon isotope value is of the Earth, of the mantle, -5, relative to the rest of the solar system, right? So what you see here is the canonical view of why there are light carbon isotopes in diamonds, right? But I also wonder, is it possible that there are high pressure and high temperature fractionation mechanisms that will cause differences in the carbon isotope values? So I don't know if you guys saw, there was a paper recently in PNAS where they found a light carbon isotope signature in graphite. This is a Mark Harrison paper. And they said that it had to be formed because of life, because it was so light, right? Well, in my opinion, and in this paper I wrote with Bernie Wood a few years ago, we suggest that it's possible that there are some high temperature and high pressure fractionations that could also be occurring in the deep mantle. But this is purely hypothetical. We have not done the experiments, right? So just as a word of caution to say that just because you have light values doesn't mean it has to be subducted organic material, but there's a lot of good evidence suggesting that in this case, most of it is. Does that make sense? Okay. Yeah.
Can you discuss the origin of the very light carbon in chondrites? The shift to light carbon values?
So chondrites you have to be careful with because it's very hard to take the difference, to separate the difference in the carbon isotopes of the organic material versus that of like the graphite or the iron carbide. And so that's why there's such a large range here, because it incorporates all of those together. But Peter Dines has a great paper on this in 2002 that I can show you that kind of tries to break it up more.
Do the enstatite chondrites, on one side or the other of the chondrite band?
You know what? For carbon, I'm not sure. I'll show you values for silicon that show what the enstatite chondrites show, but for carbon, I don't remember off the top of my head.
The reason I ask is because some of these earliest zircons may have formed as a result of early impact melts, in which case chondrites may well have been in the environment with their light carbon available. So
that makes sense.
Sorry, I'm just curious where these estimates come from, and are they more biased to shallow? I mean, they're shallow samples for the other bodies, right? And the Earth has more deep sample.
Yeah, so that's the idea. The idea is that the reason we plotted it like this is because, and a lot of this comes from Monica Grady's work, is because the Earth has a high pressure core formation, and it's possible that we, unlike these other bodies, we got this difference because of a high pressure core formation scenario, whereas these smaller bodies didn't have that. So the idea is that maybe the -5 is a result of carbon going into the core.
But there's no bias on the types of samples that you have for these?
That's a good question. Well, the Earth's -5 is the mantle, right? So that's basically everything that we have. So we have basaltic signatures from Mars, right? Martian meteorites. Vesta, it's also the HED meteorites, which also have mantle. And chondrite, like I said, has this huge range because it has everything, the organics, the graphite, the iron, everything kind of together. But my point in showing this to you is to basically say that you need to be careful when you read that just because something has a certain isotopic signature, it means it definitely occurred through this one process. Because as we can see, as I will show you, the more and more we learn about stable isotope geochemistry, especially at high pressure and temperature conditions, the more we realize that it's not as cut and dry as we once thought it was.
Well, some iron meteorites sometimes have a small amount of a phase called cohenite.
Yeah.
Was it
Fe3C.
Has anyone looked at the carbon in cohenite?
Yeah. So Dines and Wickman in 1973 looked at the fractionation between. They separated the cohenite from the graphite, and they looked at the carbon isotope difference between the cohenite and the graphite, and it's approximately like 12 per mil difference. And that's how they were able to get the temperature of the formation of that iron meteorite. And we're currently trying to reproduce that in the lab to see if we get the same values. Okay, so if we go back to this O'Neill 1986 paper, we see, again, I want to highlight, abundances are high enough that we can measure them, right? And low atomic mass. 1999 comes around, and people start getting these into their labs. Okay, this is a multiple collector inductively coupled plasma source mass spectrometer, MCICPMS. Okay, and what this amazing instrument can do that wasn't able to be done before is that it can ionize lots more of the elements than was able to be done before, and therefore more of the periodic table is then. Do you have a question?
Oh, no, I just think it's useful to tell the students why these 5 elements you mentioned earlier were so well characterized: carbon, oxygen, sulfur, nitrogen.
What do you mean?
We could ionize them easily.
Oh, right.
Prior to the development of.
That's right.
Yeah.
That's right. And so now we can ionize way more elements than we were able to ionize before. Okay, so this is an argon plasma, and argon has a high ionization potential, and so it can ionize everything in the periodic table below it. So instead of just these yellow isotopes or elements, these are just the studies over the last 5 or 6 or 7 years that people have started to measure. So these are called the non-traditional stable isotopes. Okay, it's basically everything other than the top 5, and basically anything that has more than one stable isotope will at some point be measured. Another thing that I want to add is that we not only can now measure more isotopes, right, because of the multi-collector ICP-MS, but we now also are looking at higher temperature processes, because not only can we ionize more samples, but we have better precision. Okay, so now we can look for smaller signatures, and those smaller signatures are ones that you would expect at higher temperature. But in order to know what the equilibrium fractionation is at those higher temperatures, you need to do work in the lab. So a lot of the work in the past, I said Bob Clayton's group did a lot of work in the 70s. They worked in the piston cylinder at low pressure. Okay, so we still do that now. We work in the piston cylinder. This is Craig Manning's piston cylinder at UCLA, where I did my PhD. And so you can do experiments in the piston cylinder at lower pressure. You can then go to the multi-anvil and do experiments at higher pressure. This is phase multi-anvil at the Geophysical Lab. Or, and I'll show you at the very end, you can do experiments in the diamond anvil cell and really go to super high pressure. Okay, so by being able to calibrate in the lab the fractionation factors, you can now understand more and more what we're learning from natural samples. Now, because we can measure so many different elements now that we couldn't measure before, and because our precision is so much better, what you can imagine over the past 10 years is that people have gone out and measured tons and tons and tons of rocks for tons and tons and tons of isotopes. And this database has just exploded, okay? It's not to say that we know what it means when we find fractionations in a lot of these rocks, but now we can start to tease out through experiments and through more careful separation, more careful picking of samples, right, what it means. So an example for iron isotopes in rocks. I don't have citations, sorry. This is from Craddock and Dauphin and Warren, and this is from Young et al. 2015. So what you see is that when we look at iron isotopes in rocks, chondrites are approximately at 0. Now we're assuming that the Earth is chondritic. We can have a whole discussion whether or not that's true in terms of stable isotopes, but for the next hour, just assume the Earth is chondritic for stable isotopes, okay? So chondrites are basically at 0 relative to the standard. Peridotites, abyssal peridotites in this case, are basically 0, okay? So, and morbs are 0.1 per mil heavy. 0.1 per mil in iron is considered very heavy, okay? So what we see is that the Earth, or the bulk silicate Earth, right, is chondritic, and that morbs are slightly heavy. Why are morbs heavy? We're not exactly sure. Partial melting, maybe. That's kind of the main one. Maybe an oxidation effect. Maybe there's a 3+, 2+ effect. But morbs have been shown to be slightly heavy. When we look slightly more closely at minerals, and we look at intermineral fractionations, we see that it's a big mess, right? There's no clear, consistent one mineral is lighter than another. And some of these are pretty old, and so 10 years in non-traditional stable isotope geochemistry is a really long time, okay, because a lot has changed. But so our precision has gotten slightly better, but you can see that even today, there's no clear intermineral fractionation. And this is why I said in the beginning that equilibrium intermineral fractionations are so important, because I can tell you from the lab which one of these should be lighter and which one should be heavier. So if you then go into nature and you find that it's the opposite, you need an explanation for why. What kinetic process caused that fractionation? And so one of the things that we've tried to do is exactly what I just said. Go into the lab and see which mineral should be heavier than the other, right? So if you look at, for example, phaelite and magnetite, okay, I can't stress this enough. So much of stable isotope geochemistry is a function of mineralogy. Okay? Mineralogy is like the number one most important thing you need to understand because it's all about bonds. It's all about what elements are there and what the bond strengths are. So phaelite and magnetite. In phaelite, we have iron 2+ in octahedral coordination. Okay? In magnetite, we have iron 3+ in tetrahedral coordination. Remember, lower coordination number and higher oxidation state incorporate the heavy isotopes. And we have iron 2+ and 3+ in octahedral coordination. So here we have only 2+ and octahedral coordination only. Here we have 2+ and 3+ and octahedral and tetrahedral coordination. Therefore, the magnetite should be more enriched in iron 57 than the phaelite, according to the theory that I explained to you at the very beginning of the talk, right? So we went into the lab and we conducted these experiments. The cool part about looking at phaelite and magnetite is that you're on a buffer, okay? You're on the quartz phaelite magnetite buffer. So your FO2 is not changing in your capsule because you're seated on the buffer. And so you go into the lab, make a little capsule, you put different minerals in it, you put it in the piston cylinder at a certain pressure and temperature. You get beautiful crystals at the end where this is quartz, magnetite, phaelite. You then physically separate these crystals, okay? So you smash them up and you physically separate them, and then each one you put through the mass spectrometer after you remove all other elements other than iron, okay, in the clean lab. And you end up with a thermometer, basically, right? So you end up with the fractionation between magnetite and phaelite as a function of temperature. The pink line is a best fit through the pink dots, which are the 3 experiments. And the black lines are 2 theoretical calculations that were done the year before the experiments were done. Okay, so in this case, voila, you get this perfect fractionation that it goes exactly where the theory predicts, and you see that the theory is correct, right? Magnetite is heavier than phaelite. So if you go to a rock and you find magnetite and phaelite, and that isn't the case, or it doesn't show the right temperature that you would predict from another thermometer, then you need to explain why.
What's the actual temperature range there of the experiments?
600 to 800 C.
Did you use pure phaelite, or is it just the phaelite component?
This is pure phaelite. Okay, so another example is silicon isotopes. Okay, so as of 2 years ago, silicon isotopes showed this histogram or probability density function, right? So the mantle, morb, OIBs, and basalts all kind of agreed with each other in this one range, where this gray box represents the bulk silicate earth value plus the error. Okay, so everything was basically the same. If you look more closely, so this is the Earth. If you look at undifferentiated and differentiated objects, you see that they're slightly offset, where this, again, is the bulk silicate Earth. You can see the moon is exactly the bulk silicate Earth. But chondrites and differentiated objects are not. Okay? So the moon equals the Earth, or the bulk silicate Earth, but chondrites do not, and chondrites equal Mars, equal Vesta, etc. So this, at first glance, was what people used to suggest that there's a core, silicon isotopes in the core, okay, that cause this difference between bulk silicate Earth and chondrite, and that it has to have happened at high pressure because these objects, such as Vesta and Mars, you don't see that. So there would be no silicon isotopes in the core of Vesta or Mars in this case, but there would be on Earth. And that the moon inherited the signature post-core formation of the mantle of the Earth. Now this is simplified, obviously, because there are lots of other reasons that you can fractionate silicon isotopes. But this was one of the first high-temperature applications of stable isotope geochemistry. One of the first times that we could say that even at a 3,000 Kelvin, you still would have a fractionation of your stable isotopes. And then last week, Matt Jackson is a co-author on this paper. This article's still in press. Emily Pringle, who's a PhD student at IPGP, this paper just came out where they've looked at samples more selectively, right? They're not just measuring all samples. They're looking in particular at OIBs. And what they find is that there are some that are actually lighter than that bulk silicate earth value that I showed you earlier. So while in the past people just kind of measured everything, right, and didn't see much of a trend, now we're looking more closely at rocks, and now we're saying, okay, well look, these OIBs are lighter than the bulk silicate earth. One of the reasons that
And now, could you go back to that previous slide and then one? So the lighter here means -0.1.
so they've, for some reason, changed the axis here. Is that what you're asking?
Yeah, just because they're on different figures, it's hard to compare this with the previous slide.
So normally, you plot the delta values relative to a standard, okay? And relative to the international standard, the Earth is at -0.3. And I noticed this morning. For some reason, I don't know if you know why, she chose to put to put that standard here and to make the Earth 0 as the standard. I have no idea why, but you can see that 0.3 difference. Here is that international standard that we normally, I have no idea why that happened, but.
So if you go back one slide, it looks like that, these are, when people are measuring anything, it looked like these sigma here on this measurement or on the range of variability that we see is about, 0.05, right? So it goes from like -0.4 to -0.2. And then if you go to the next slide, there's this very small gray part that's shaded around 0.
Yeah.
And it seems to me that if you just draw samples at random from a distribution that has a sigma of around 0.5, that you could see things that are 0.1 and you wouldn't be too surprised. Should we take this to be an indication of, has like the precision improved or something like that?
So these data are all data that were ever published on silicon isotopes from all sorts of different labs. I'm being recorded, but all stable isotope geochemists think that they have the best precision and that they do things better than everybody else, right? So this is everybody's data, and over probably 5 or 6 years. These are her data from her lab with her internal precision on her mass spectrometer, right? And so her errors you should take as face value. These are the errors that she reports, and we're going to assume that that is what they are. So within these data, this is clearly lighter than this. But you're right on another point, which is that we're looking at very small numbers, right? And so on some level, we need to be slightly careful that we don't overinterpret very, very small numbers. But this, when I saw this paper last night, I think this is clearly different, right?
Sorry, to clarify, my question was about the width of the gray bar around BSE.
Yeah, so
is that supposed to represent the range of within
the bulk silicate earth? Yeah, right. So there was a lot of controversy for many years about the value of the bulk silicate earth. So here, Paul is being very conservative and making sure that everybody's data are there, whereas here, this is a more probably correct estimate of what we think the bulk silicate earth is.
You have two measurements here in the same. Mangaya, you have two measurements. One is outside the range, and
do you know why, Matt? Why Mangaya has one light and one?
Oh. We're not sure, but we attribute the shift to a recycling process because shallow. Oh, you're going to get to this. But before you do that, can I explain that why it's referenced to.
Oh yeah, I was wondering why it was referenced to bulk silicon. Yeah.
So first, the samples are normalized to the standard, right? The NBS standard that's run with daily, constantly, like in between the samples.
Yeah.
But then also by a BHVO of a salt, right? So that would actually give you a better estimate of a real sample that you're running through the columns and then running on the mass spectrometer. It's not a
So they have
it's
two
not a pure
standards
metal.
that they're running. One, which is an internal standard that they're running through the mass spectrometer after every sample, and then one standard that they also run through the column to make sure that they don't fractionate through the column in the clean lab. And so because there are two standards, it's easier to just,
Yeah,
is that right?
So BHVO would be like BSE.
Yeah.
Yeah.
Yes.
I have a question on the last slide.
Is that this?
With
this one?
Mars, that one.
Okay.
Why is Mars so different from the Moon and the Earth? Because the Mars, I would assume, have an iron core.
The idea that we've proposed is that Mars, so the light element in the core is a function of many things, including temperature, pressure, and oxygen fugacity. And so it's thought that Mars was not at low enough oxygen fugacity and that it doesn't have silicon in its core. It probably has sulfur in its core, whereas Earth has silicon in its core. And therefore, the fractionation during core formation of the silicon is what you're seeing here. Whereas for Mars, all of the silicon is still chondritic and therefore all in the mantle.
So is that why the Moon is more similar to the Earth, because of that same reasoning?
So it gets complicated because, yes, the moon is thought to, so the easy way of looking at it, right, the oversimplified way of looking at it, I should say, is that when the moon formed from the giant impact, the Earth had already fractionated its silicon isotopes, and the moon inherited the silicon isotopic composition of the mantle. Whether or not that's dynamically possible, I have no idea, because there are lots of things that happen when a mantle, when you have a huge, giant impact, right? But that was the original thinking. Okay, so what Matt just said is that the reason that these values are light, they think, is because of a recycled component. Okay, and so what they've done here is they're showing you this bulk silicate Earth value again, and the amount of the recycled component, assuming that 3 different values for the silicon isotope value of the recycled component. Okay, and what you're seeing is that if you have a recycled component that's lighter, then you could be seeing that in the OIBs. Okay, so it's possibly tapping into a heterogeneous mantle. In the paper, they also mention this paper, which was published a couple years ago, which is a theoretical paper, DFT calculations, where they've calculated what the silicon isotope fractionation would be between minerals at high pressure and temperature. They suggest in their paper, and in my opinion correctly so, that this is not the reason for the values that they're showing, that they see, the light values that they're seeing. But I just wanted to show you this because we keep looking at these types of schematic diagrams over the last couple of days. So I just want to show you the isotope version of it, right? So what they've done is they've calculated the fractionation between 2 minerals, so mineral minus olivine. So olivine's always the second, as a function of temperature. And then they've put it into this schematic diagram. So what they're showing is that the upper mantle has a different silicon isotope fractionation because bridgmanite, right, is so light that it brings during the crystallization of the magma ocean, bridgmanite would have sucked up the light silicon isotopes, and therefore the whole bulk silicate Earth is actually slightly lighter than what we think when we measure the upper mantle. But in the Pringle et al. Paper, they suggest this is not the reason for what they're saying, and they suggest that it's a recycled component. Okay.
I'm very unclear about what recycled mean. Recycling what?
Recycled oceanic crust, right, Matt?
And that would mean that recycled oceanic crust has a lower,
the sediments or not the sediments, the recycled oceanic crust itself would have a lower value. Plus some sediments.
And why would that have a lower value relative to everything else to begin with?
Why would the silicon isotopes? Because it's...
So low temperature surface alteration will give you the most extreme, some of the most extreme isotopic, stable isotopic comforts.
Biologic?
Yes, cherts are quite light as well.
So
that's right.
That would be the biogenic fraction.
It's the same as with carbon. Anytime you take something from the surface, it's going to have a much larger fractionation because it's at low temperature and when you bring it down. Except in this case, it's not necessarily biology, as it is with carbon, but just low temperature fractionations.
Or with oxygen, right? You don't get
oxygen.
A lot of oxygen isotopic fractionation at high temperatures in the mantle, high temperatures and pressures. But when we see wide variability of oxygen isotopes in pristine lavas being erupted at the surface, we have really good evidence that that fractionation, but we're seeing fractionations that could only have happened at the surface in deep time. So stuff had to go down and come back up again, because you couldn't get those fractionations in the mantle.
So this is very exciting because it shows for one of the first times, right? There have been hints of this, in oxygen or magnesium, or one paper on calcium. But this is one of the first times where the recycled component, they think, is really being seen in these non-traditional stable isotopes. Yes?
Our question is that, so in the carbon isotopes, and we can also see the information about recycled, how well it's recycled. And here we also have this information. Is it consistent with the previous carbon information from carbon?
So I think in this paper they mentioned it's consistent with oxygen. I'm not sure they discuss carbon. But in the paper they mentioned that it is consistent also with oxygen. Okay, so that's silicon. Now we're going to focus on iron. So a lot of the work done in non-traditional stable isotopes has focused on iron, because iron was really the element that was most hard to ionize previously before this multi-collector ICP-MS. It's very, very difficult to ionize. And so if you think back to the reasons why isotopes fractionated, one of the reasons that Edwin pointed out was a low spin configuration he wrote, but then he wrote this was largely untested, right? So this is the only paper I know of that's tested whether or not a spin transition will cause a difference in the isotopes. This is, again, a DFT. These are DFT calculations. These are not experiments. So what they're showing is pressure going down. So imagine you're going deep into the Earth. And this is that beta factor, right? So this is basically the fractionation. In order to get the fractionation between two, you just subtract. So this one minus this one will give you a fractionation of about 0.1 per mil, okay? So what you see is FEP, which is ferropericlase, basically FeMgO, right? High spin, low spin, and then ferroperovskite or bridgmanite with iron in it, high spin or intermediate spin. And what they do is for 3 different temperatures, so when you're calculating isotope fractionation, you need to choose a temperature. Same with in the lab, right? You have to do it at one temperature and then kind of extrapolate between them. And what they've done is they're looking at whether or not the spin transition causes a difference in their isotopes. And what they see is that for ferropericlase high spin, right, and then it goes to low spin, you see that the difference between the ferropericlase and the perovskite at low pressure is much higher than it is at high pressure. So the spin transition does cause a difference in the isotopes, and in this case, it causes the isotopes to be more similar at high pressure than it is at low pressure. This is actually backwards from what Edwin predicted, but again, there are no actual experiments. These are DFT calculations. So what they did is they then took these, right, and using these gray lines are basically the thermal gradient that they say you might expect in the mantle. They then took this and they made a fake crystallization sequence for a magma ocean. So first starting out at high pressure and temperature and then kind of making your way up. And what they show is that the fractionation, they say that there's this difference in the iron isotope fractionation in the deep mantle compared to the upper mantle. And they use this schematic figure in order to say, well, maybe one day we'll be able to see that value because it's still stuck in a reservoir at the bottom of the mantle, and maybe we'll be able to see this value at some point. So again, morbs are heavy, right? We talked about this earlier. Morbs are heavy relative to peridotite. And so there have been people who have suggested that maybe that's a high-pressure iron isotope signature in the mantle. Okay, so that's DFT calculations. What about experiments? So there are, as I mentioned before, there are different things that we can change in the lab, different variables that we can change in the lab that will give us different constraints on which variables are more important for isotope fractionation. And one of them is composition. Okay, so redox has been shown to cause an isotope fractionation, as I showed you with the phthalate magnetite experiments, right? And coordination number, the 3+ and the coordination number. But what about composition? What about what elements are actually bonded? And so what we've done in these experiments is we are looking at the iron isotope fractionation between metal and silicate as you add more sulfur to your metal. So this is more of a Mars sort of scenario, okay? And what we found is that the fractionation increases the more sulfur you put into your metal. This was completely a surprise, and the reason is that, so when Edwin wrote his chapter in 2004, when he wrote that these values are, or these predictions are untested, he then continues and says that it's unclear which ones will win, right? So people always think that temperature is the most important variable when it comes to isotope fractionation. And I showed you that in an equation earlier, right? It's 1/t². So that's pretty important, right? That's going to cause a very strong decrease in isotope fractionation. But composition was thought to not be so important. And so when we did these experiments, we didn't expect to find a dependence on the sulfur content of the metal. So then we tried to figure out why. And remember I told you mineralogy is very important, right? So as Uli was saying earlier, a lot of this work was done for metallurgy, right? So what do you do when you don't know what's going on? You go back into the literature, right? And you pick up a textbook on metallurgy because they understand much more about the structures of alloys than I do. And you read this book. And what you find is that there are two different kinds of alloys. Or substitutions in alloys. There's a substitutional effect where you actually swap out one element for another, right? And there's an interstitial where you put an element in between elements that are already there. And the way you know which one's which is its size, right? If it's small enough, it'll fit in those interstices. And if it's big, it'll knock out an iron and get into its place. Yes?
So does the mob has more sulfur in it because of sediments or something?
Does what have more sulfur?
The mob oceanic crust has more sulfur in it, and because it has also is also heavy in iron. So and you show is a big good correlation.
So I don't think it has that much sulfur in it. The question is whether or not the morbs are heavy because of sulfur.
Yes.
No, I don't think so. In these experiments, we're focused on cores, right? So sulfur goes into iron metal very, very readily.
Not also, though there is, both of those substitutions are in a dilute limit in the way they're phrased, and so that there can be, what is not included in there is potential interactions between the lighter alloying components, some of which there is some theory indicates could be important at high pressures and temperatures.
That's right. That's right. So the simple way, right, of looking at this is basically that there's a favorable zone where the radius ratio of the element relative to iron, if it falls in this zone, then it'll be substitutional. If it falls out of this zone, it'll be an interstice, okay? But it's not this simple because sulfur, for example, is a substitutional because it's not in this zone, right? But it's very electronegative, and so it kind of pops it into that zone. And so what we find if we just do the theory is that nickel and sulfur should have substitutional, whereas oxygen, carbon, hydrogen, and nitrogen should be interstitial. And so we did the experiments on sulfur, and we thought, well, maybe that's why the sulfur causes an effect on the iron isotope fractionation, right? Maybe the more sulfur you add to the iron, you're kicking out the irons, you're adding sulfur, and you're changing the bonding. And maybe the bonding between the iron and the sulfur is stronger than the bonding between the iron and the iron. And so then we thought, okay, let's test it. If nickel is supposed to do this as well, a lot of times in experimental metrology, we add nickel into our iron because that's natural, but we assume it doesn't play much of a role in anything that's going on, right? And so in this case, we thought, well, let's test it. Let's see if nickel plays a role. And so we did experiments. So these are the ones I showed you earlier with the sulfur, right? The gray ones. Except this time, we're looking at atomic percent. The last plot was weight percent. So these are the total substitutional elements. Okay, so here we did experiments with carbon, which is not substitutional, and we find there's no fractionation between the metal and the silicate. With the sulfur, we found there was, and then we did it with nickel, these blue squares, and we find that again there is this fractionation. Okay, so the point of me showing you this is to tell you that to prove to you that composition can also have a large effect on isotope fractionation. Yeah.
For the nickel experiments, why did you also use carbon in that alloy?
Because we used a graphite capsule. The bane of my existence is capsules. They're the most frustrating because they always interact with your experiment. And so when you try to do experiments in other capsules, for example, MgO is a typical one, you have a lot of interaction between the iron and the magnesium, and you lose iron from your system. So your system is no longer closed. Graphite is nice because the iron is contained, but you get graphite in your system. We tried boron nitride as well, but the FO2 is so low that you basically get no iron in your silicate. And so there are trade-offs. And so the reason we did the ones with just carbon and no nickel is to prove to ourselves that it's not the carbon that's causing this, it's the nickel.
So why not for the sulfur experiments?
Why not carbon?
Yeah.
We did those experiments in boron nitride capsules because the sulfur helps the FO2. So you still get some iron in your silicate. There's a lot of trade-offs when you do experiments, right? Okay, so the point is that we've now proven to ourselves that composition can affect isotope fractionation even at high temperature. So we have all sorts of different ways that the isotopes can be affected even at high temperature. I'm going to skip sulfur. Okay, just real fast. So the only thing I want you to get away from this plot is that sulfur isotopes are different between chondrites and mantle. Okay, so a lot of this non-traditional stable isotope work recently has focused on whether or not the Earth is chondritic. So in this paper, they show that the mantle sulfur isotopic composition is different than chondritic. That's all I want you to get away from that. Don't worry about anything else. But again, what you do is you do experiments, right? And you say, okay, well, why is the Earth non-chondritic in its sulfur isotopes? Is it a core formation signature? Is it a partial melting signature? You don't know until you get the fractionation factors from the experiments. And so in these experiments, what Shahar1 did is he looked at the sulfur isotopic fractionation between metal and silicate. And while it changes depending on which capsule material you use, there is a fractionation, okay, between metal and silicate. But what's interesting about this is not the metal silicate fractionation, but when you start to try to understand why that fractionation exists. And it turns out that when we started playing around, because we did it in 2 different capsules, and got different answers, we then had to start playing around with compositions, right, in order to understand why there is this fractionation. And what we find is that boron and aluminum, which are network formers, right, tend to increase the fractionation of sulfur somehow. Okay, you would think instantly polymerization, but we did the experiments with silicon, and silicon has no effect on the system at all. And so there's something about boron and aluminum in these silicate melts that's causing the bonding of sulfur to be different in the melt. So I bring this up because we mentioned earlier how Lars had done calculations where they've looked at how melts have different structures throughout the mantle, right? Silicate melts have different structures throughout the mantle. That should be visible with isotopes, okay? And this is an example of that. Okay, and finally, my last example is that I have completely neglected pressure in everything I've talked about thus far, okay? And the reason is here. I said Bob Clayton and his colleagues at Chicago had done a lot of experiments looking at isotope fractionation at high pressure and temperature in the 70s. And they did a lot of their experiments in the piston cylinder because it was easier to contain everything in a capsule, and reaction rates were faster at the higher pressure and temperatures. Okay, so they were able to contain it all, and that's why they did it in the piston cylinder. But they also wanted to make sure there was no pressure effect, because then the idea of doing the piston cylinder would no longer be effective. And so what they did is they looked at the isotope fractionation of oxygen between calcite or aragonite and water as a function of pressure. Pressure here goes up to 20 kilobars, which is 2 GPa. Okay? And what they see is that there is no effective pressure on the isotope fractionation. So because of this paper, for the next 40 years, correctly, people assumed that there was no pressure effect. Because it's true, at up to 20 kilobars, there is no pressure effect. But what happens if you go to higher pressure? Should there be an isotope effect? And there are 2 main options or possibilities for why there might be a pressure effect on isotopes. The first is called the molar volume isotope effect. Okay? The change in the fractionation factor as a function of pressure at constant temperature is a function of volume. Because you have that extra neutron in there, your volume can change between your isotopes. Turns out it's really, really, really small and not something that we're able to measure or ever see in the lab. However, as you squeeze things, the bonds stiffen. Okay? And what we showed earlier is that stiffening of the bonds causes a difference in the isotopes, right? This, it turns out, can be seen. This cannot, at least in systems that don't have water. Okay? Water is a special beast. But this can be seen. Okay. But in order to do that, you have to use a diamond anvil cell. And everything I've showed you so far, right, is how you take a mineral from a rock or a mineral from an experiment, and you separate it from another mineral, and you put it through columns, and you put it through the mass spectrometer, and you look at the difference between the 2. But when you're working in the diamond anvil cell, you don't have the luxury of separating 2 different phases, right, post-experiment. That's just not an option. There's not enough material there for you to separate mechanically, put through the columns, and then put through the mass spectrometer. At least not yet, right? You never know. And so what you have to do is you have to get creative. And this is where interdisciplinary science is so important. And I bring this up because I'm speaking to a very interdisciplinary group, right? I'm an isotope geochemist, and I don't normally go to places like the synchrotron to do experiments or use diamond anvil cells, right? But because you speak to people in different fields, you learn that different techniques that they use could actually be useful for your own science. So there's a technique at the synchrotron called nuclear resonant inelastic X-ray scattering. And mineral physicists have been using this technique for a long time. But what it does is it probes the vibrational properties of certain isotopes. Okay, so like a Mossbauer, so iron 57, it has to be certain types of certain isotopes are able to be probed. But vibrational properties are exactly what causes isotope fractionation, right? So I can go to the synchrotron and use this technique in order to probe the vibrational properties of one phase, and then I can use a different diamond cell and probe the vibrational properties of a different phase, and then I have the fractionation between the two. Okay, so I don't need to mechanically separate the two phases like I did when I was doing multi-anvil or piston cylinder experiments. I have each one separately. And what you get, so this is that same, a very similar equation to the Beagle-Eisen and Mayer one. And it has a force constant value, okay? And that force constant is what you measure at the synchrotron. And so that force constant then gets, the equation is very simple for getting the beta, which is the isotope fractionation factor, okay? And so Nicolas Dauphas at University of Chicago has done some of this work. And what he finds, so on the y-axis you'll either have force constant or isotope fractionation. They're linear basically. What he finds is that the iron force constants or isotope fractionation changes as you change the SiO2 weight percent. Okay, so as you get to very rhyolitic samples, suddenly you have a jump in your force constant. And this is also seen in natural samples. There's this trend of iron isotopes with SiO2.
This is in liquids.
This is in solid.
Or glass.
This is in glass. Yes. So they make the glass, but then you do the experiment at room temperature. He's done the same sort of thing looking at redox. So redox, we know, causes a difference in iron isotopes, but it's been very hard to experimentally determine exactly how much. And so by being able to probe one phase at a time, he's been able to go in and say, okay, well, I'm making glasses where I know from Mossbauer exactly how much iron 3 plus I have, right? And then I can look at the trend with iron 3 plus of how much the isotopes or the force constants change. And what we've done is we've done the same sort of thing, but looking at the effect of pressure. Okay, so I've always been somewhat obsessed with this idea that pressure does not have an effect on isotopes. And so we wanted to prove it to ourselves. And so what we did is we did the nuclear resonant inelastic X-ray scattering experiments, looking at iron, iron carbide, iron oxide, and iron hydride as a function of pressure. Okay? All you're seeing in this plot is that as you increase the pressure, the bonds stiffen. That's not telling you there's an isotope fractionation. It's just telling you that bonds stiffen as you increase the pressure. But because these y-axes are not all the same, you're also noticing that the slopes are different. I should have written the slopes up here, but the slopes are different for the different phases. Therefore, if you subtract them, you get an isotope fractionation between them that's different as a function of pressure. And so what we've done is we've calculated what the bridgmanite iron phase, right, fractionation is as a function of temperature for a core formation, magma ocean kind of setting. And what we see is that at high pressure, there's a fractionation between bridgmanite that changes depending on which light element is alloyed to the iron. Okay, so not only is there a pressure effect on the isotopes at very high pressure. So not to say that the Chicago group was wrong. They were absolutely right. But they only went up to 2 GPa. We've now extended that in experiments up to 50 GPa. And these green circles are theory. Okay? So we use the experiments basically to make sure the theory is accurate. And then we go out, we extrapolate with theoretical calculations to higher pressure. So there is a pressure effect on isotopes, but only at very high pressure. And if you look at the fractionation between bridgmanite and iron, you can see that it changes depending on which light element is alloyed to the iron. So if you make a cartoon of what the iron isotopic composition of the mantle would be, assuming that the only thing that affected it was core formation, you can see that these values would change depending on the light element that's in the core. These numbers are small, but they're measurable. Okay? this value and this value maybe are not, would not be seen, but these ones would very much be seen, and we don't see them in samples, in rocks.
How much of a difference do you anticipate between bridgemanite and silicate liquid under these conditions? Because the equilibrium here would likely be with the silicate liquid rather than with bridgemanite.
Yeah, so it's like you reviewed the paper or something. So, silicate liquid is the holy grail for doing this. The problem is that, and you probably understand this much more than me, that you start to get really large anharmonic effects as you get to those high temperatures in the diamond cell, especially, right, at high pressure. And everything that I showed you, all the theory I showed you at the beginning, is all assuming a harmonic oscillator, okay? And as you get to these really high pressures and temperatures, that's no longer valid.
And it's even a little worse, because often the first nearest neighbor distances in liquids often increase. And the compaction of the liquid is taken up by second nearest neighbor and further out measures. The simplest example of that is things like silicon going from 4 to 6-fold. That's actually a weakening of the SiO bond.
That's right.
And Fe going from octahedral coordination to dodecahedral coordination, that's a weakening of the FeO bond.
That's right, which will lower the fractionation difference. That's right. And so, that's right. I agree completely with everything he said. And so one day we will be able to do the melt as well experimentally, but it's really hard because you need to laser heat and you need to have a stable temperature, or else the isotopes go totally bonkers, right? So I'd like to do the melt experiment at some point. Nicola has tried to do, they had an AGU abstract this year where they melted it into a glass, and then they did the NRIX on the glass. And they also find that there's a large pressure effect, but smaller than what we find. So, with 5 minutes to spare, I'd like to leave you with a couple of things. There's been tremendous work done over the past 10 to 15 years on these non-traditional stable isotope systems and on the traditional stable isotope systems for many, many decades, right? There are a lot of questions because the better our precision gets, the more differences we find in natural samples, right? And understanding what that means, and if it means anything at all, is really important and something that I think will take several decades to kind of work out. So there's tremendous opportunity in these fields because everything that I just showed you, I mean, is probably half of the papers that talk about the deep Earth with respect to isotopes. There just isn't that much. So there are lots and lots and lots of questions that still need to be answered. But I hope you've taken away that the basic premise that stable isotopes are a wonderful tracer for different processes if we just understand how they work. So with that, I'll take any more questions.
Let's have the first question from a student so we can wait uncomfortably until someone asks a question.
Here's lunch. There we go. Yes.
But we have 2 students.
Wait, where's the other one?
Yes, to come back to the anharmonicity problem, in DFT calculations, are they molecular dynamics? So
which ones?
The DFT calculations.
For iron?
Yes, for example. I mean, if...
These?
Yeah.
These are Razvan's
yes.
calculations.
Oh, so it's not.
PhD advisor, yeah.
Yes, but if you in a molecular dynamics calculation, you include anharmonicity.
Yes.
So, is it the post-processing which considers only an harmonic model, or
no? It's just the theory, not the DFT calculations. The theory that I spent the first 20 slides on, right? That assumes a harmonic oscillator. These are just they are what they are, right? Because this is what we measure in the lab.
So this is just how from this you goes to the partitioning.
Right. Jonathan.
So you showed one example with the silicon isotopes through the Earth as a function of depth in a cartoon sort of form. So my question is, what would it take to be able to create a sort of a geochemical tomography of the mantle?
That's an interesting question. You would basically take the mineralogy and you would put the geochemistry on top of it. So if we knew that we need to know where the minerals are, and then we would put on top of that the isotope fractionation associated with it. But we need to be slightly careful with those sorts of models because it assumes that you have, okay, your reservoir of silicon isotopes is fixed on Earth, let's say, right? And you have this crystallization sequence, but what you're assuming is that as the perovskite is crystallizing, it's got this infinite reservoir of whatever your fractal melts, let's say, surrounding it, right? Isotopically speaking. And then it's going down. And then every perovskite that's crystallizing is also seeing the same equilibrium melt as it's crystallizing. And then and the same for the rest of the mantle, right? So it's assuming this very simple equilibrium fractionation, which then stays and doesn't at all fractionate again until somehow it gets brought up into a plume and we see it on the surface. I'm not sure that's physically correct, but if we knew where all the minerals were and what the fractionations were between all the minerals at the high pressure temperature conditions, then we could at least have a starting point for where the Earth started and then kind of create models for where it would be today.
So then to what extent should these deeper fractionations be preserved in samples we measure at the surface?
I have no idea. I think that's a really open question right now. The values are small, the fractionations are small, but they're real. And there are many ways to change them. So it really, the way I look at it is that we need more and more and more experiments, just like they did with oxygen, right? For decades, they just did experiments for every phase that they could come up with. And then you model it. So you basically parameterize the whole system, right? So you say, how does pressure affect it? How does composition? How does temperature? And then you parameterize the whole system, and then you can run models to see whether or not, if a fractionation occurred in lower mantle, would it be erased by the time it came to the top? I'm not sure we are yet at that point where we can answer that. Matt?
That was a lot of fun. Thank you. So 2 questions. One is, mostly because I haven't had enough coffee, what would be the per mil difference between the 2 charges you measured on the upper left-hand corner?
So that is per mil. So you just subtract them. So you mean the 2 pressure differences?
Yeah, the delta 57.
So
so that's 4 per mil.
That's 4 per mil of iron between 2 different pressures.
All right.
Yes.
Sorry. Okay. So
10 to the third natural log beta is delta.
Right. Okay, so huge differences. Cool.
Huge differences,
So,
but at room temperature.
So you offered this tantalizing hypothesis, the difference in the silicon isotopic composition of the silicate Earth and other bodies in the solar system could be due to silicon isotopic fractionation during core formation. And can you tell us a little bit about experimental constraints?
I did those experiments. So there are 2 experimental papers, one by me, where we find the difference between metal and silicate for silicon isotopes, and then we look at the difference between bulk silicate earth and chondrite. And if you do a very simple calculation where you say that the only fractionation that could have caused the difference between bulk silicate earth and chondrite is core formation, then you would end up with about 6 weight % silicon in the core, which is approximately in the right realm as some geophysics models. There was another paper published a couple years later which had a much different fractionation, almost zero. And which one's right? And if they're right, then there must be another reason for the difference between chondrite and Earth that's not core formation. There are also a lot of complexities with what different meteorite groups show. Some people have used the fact that enstite chondrites are really, really light to prove that the Earth is not made from enstite chondrites. But there are all sorts of games you can play with these values. But to get to Matt's point, there are many ways to fractionate silicon isotopes, and not all of it is probably due to core formation. And you need more than just 2 experimental studies to get at what the fractionation is, because in our 2 experimental studies, we had 2 completely different compositions, because at the time, nobody thought composition mattered, right? Fast forward 5 or 6 years, suddenly we realize composition has a huge effect. So you can think of this community as if the partitioning community, where partition coefficients, right, are very similar to isotope fractionations, and how long the partitioning community has done experiments and changed one variable at a time, and how different experimental papers are from one another, and how over time we've been able to parameterize it. The isotope community, the stable isotope community, is now in that same boat, but just many, many years behind, if that makes sense.
Question. Your rule of thumb and the equations that describe isotope fractionation between phases suggest a pretty direct relationship with the elastic constants and the fractionation factors.
Yeah.
And so I'm wondering if it's possible to just look at the bulk moduli at pressures and temperatures and get order of magnitude, predictions for fractionation factors between different phases.
So that's a good point. So in the Young et al. Paper that we published last year, Ed goes into a lot of detail about how you could just use Pauling's rules. We keep coming back to Pauling's rules. You can get a pretty good order of magnitude and direction of fractionation just from using Pauling's rules and from looking at the bonding of the environment. I'm not sure we've ever done it for high pressure, but we should and see what we get. There, he was only concerned about bonding environments and temperature.
But it's first nearest neighbor distance versus bulk crystal, and those can be dramatically different.
Right, that's a good point.
But does the nuclear resonance X-ray scattering measures force constants, not nearest neighbor distance?
Force constant for
but
iron.
you alluded to, but that's the local vibrational environment of the iron atom as opposed to the bulk compressibility of the crystal. And those originate from two very different phenomena. I mean, they're related, but it's not a simple correlation.
Great, thanks. Right. Lunchtime?